All right, here is question 7, and the next question 8 is pretty easy, but this question is pretty tough. They want to know the acceleration of the 4 kilogram block. What we need to know is the acceleration of the 4 kilogram block. All of it's accelerating at the same, so it's really asking what's the acceleration of the system. Always start with a free body diagram. So this one's got a weight of negative 40 newtons, and this one's, and there's a tension here pulling up, and then there's a tension here. Oh, there's two tensions, so that one's 1, that one's 1. Actually, yeah, that's tension's pulling that way, and this tension is, I'm sorry, pulling this way. And then there's a tension here pulling this way, and a tension pulling on the bottom of this block. Those are the same. And then there's a weight here of 20 newtons and a weight here of 10 newtons. All right, and so the tensions are going to cancel. If it's a frictionless massless pulley, ha ha ha, right, then that tension will cancel that tension, and that tension will cancel that tension. It's important to know that when we get to the a later unit, when we're doing rotational motion, we're going to stop pretending that the pulley doesn't matter, and then that's going to change, and the tensions aren't going to cancel each other anymore. So I just want to warn you ahead of time that you're going to see that later on in the semester, second semester. All right, so now I've got my free body diagrams going over here. I need to know acceleration, and that's going to be equal to the net force divided by the mass. Well, another thing I need to do for a pulley problem like this is I have to decide which way is positive. So see, I've got 30 over here, so I'm pretty sure I always do positive in the direction of motion. So I'm going to say everything going this way is positive, and everything going that way is negative. So this one's positive, and this one's negative, and this one's positive, so you can see they cancel. And let's see, this one's positive, and this one's negative, and they cancel. And this is negative, and that's negative, because they're going this way. Anti-clockwise is negative, and clockwise is positive. All right, so the net force is 40 minus 10 minus 20, which is equal to 10 newtons. And that's divided by the mass, but it's the mass of all of it. It's a system, 4, 5, 6, 7 kilograms. So the acceleration is equal to 10 newtons divided by 7 kilograms. So this is called an Atwood machine problem. And normal year, we would be super familiar with this. Well, in past years, I don't know. Right, I'm trying to change the way that I teach this class so that it is actually aligned with the new paradigm. But this is called an Atwood machine, and there it is. So it doesn't matter really for the purposes of this first part of the problem whether this is 3 kilograms, one thing that's 3 kilograms, or two separate things. But it will matter for the tensions. All right, so now to find the tension in the this string right here, we have to just look at this piece of the system by itself. So if we look at that piece of the system by itself, we can see that the net force is equal to 40 minus the tension, right, the two forces, and that's equal to the mass, which is 4 kilograms. We're just looking in the box, times the acceleration, which we just decided was 1.4, right, because net force is equal to mass times acceleration. That's Newton's second law. So we only have one thing that we don't know, so we can multiply the acceleration by 4. So we can say 40 minus the tension is equal to 5.71 newtons. So if we do a little algebra, it would be, we could just say minus 40 and then change the sign in our head. The tension is equal to 34 newtons-ish, rounds off. And if we looked at the tension on this side, we could discover that it would be a much more difficult problem to do that. Because this has got so many things on it. So when we analyze the system, we really want to avoid looking at the 2 kilogram object because it's got two different tensions on it and it's a mess. If we want to find the tension on the 1 kilogram object, then we just look at the 1 kilogram object. So we just do this work down here below the green line. And again, now it's important to make sure that we write positive tension minus 10 newtons. See how it's different? Because of the signs that we established at the beginning of the problem. We can't just change them willy-nilly because of how we feel about it. Okay, we have to keep the signs the same and consistent throughout the whole problem. That was positive. at the beginning of the problem, so it's still positive. And this is equal to the mass, which is 1 kilogram, times the acceleration. So get out your calculator, multiply 1 by 1.4. I'm going to do it in my head. Oops. Minus equals 1.4 newtons. So T2 is equal to 11.4 newtons. So the tension here is 11.4, and the tension here and here is 34. And that is not the end of the story. The kinetic energy of the system after 1 second. I guess there's probably some different ways to do it, but we could try to figure out what the speed is after 1 second, and we know the acceleration, we know it starts from rest. We can find the final velocity at time equals 1 second. So that's going to be VF equals V naught plus AT. So that's equal to 0 plus 1.4 times 1, 1.4. So the kinetic energy is equal to 1. The kinetic energy of what? The system is 4, 5, 6, 7 kilograms times 1.4 squared. So I'm going to let you go ahead and use your calculator to calculate the kinetic energy. I don't feel like doing it. All right, number 8. The spring is stretched 10 centimeters with 20 newtons of force. What's the spring constant of the spring? Well, this isn't really the right way to do a spring constant, but I guess it'll have to do in a pinch. We can say that the force is equal to negative kx, and that's because it's a restoring force. That's the negative sign doesn't really mean much. It just means that it's always trying to move it the opposite way than what it is actually doing. And so the 20 newtons goes here, and the k goes here, and the 0.1 meters goes here, and then k is equal to 20 divided by 0.1, which I just really wish I could do that in my head, but I just don't trust my head. 200 newtons divided by meters is the unit. And the proper way to do a spring constant, of course, is to collect data and make a graph of force versus x and find the slope of the line. And that's the proper way to find the spring constant, but we're just going to pretend like we could do it this way with one piece of information and be terrible scientists. The elastic energy is equal to 1/2 k x squared, so the elastic energy is equal to 1/2 times 200 times 0.1 squared. So it's equal to 100 times 0.1 squared, and so 100 times 0.1 squared is equal to 1 big old joule of energy. There you go. Number 9, where are we at? 8 minutes. You pull a box across the floor with a force of 610 newtons. Okay. The angle, we're pulling it at an angle, apparently. That's not very clear. It's 35 degrees. That's 610. There's a friction. The mass of the crate is 125, so the weight is 250 newtons. There's a normal force, which is not equal to the weight because we have this force here is pulling up as well as sideways. Right? Find the acceleration of the box and the amount of work done moving the crate a distance of 3.5 meters. All right, so there's a free body diagram. This is where we start. We always start with a free body diagram. This is the force of gravity, normal force, force of friction. So we're moving in the xy direction. So we want to find to find the acceleration, we want to know the net force in the x direction, because that's the direction of motion, divided by the mass, which is 125 kilograms. So, bibbidi bop, bibbidi boo. So in the x direction, the net force is equal to the component that's pulling in the x direction. So we're going to say 610 cosine 35. That's the adjacent side. And we're going to say right is positive, right? And then the minus the force of friction, which is force of friction. All right, well, 610 cosine of 35. The force of friction is the normal force times mu. And the normal force is, that's a hot mess is what it is. So we have to use what's going on in the y direction to find the normal force, and it's not equal to 1250 because we have a vertical component over here. So in the y direction, the net force is equal to 0 because it's not moving in the y direction. And so up we have normal force plus 610 sine of 35 minus 1250. Right, we're using G equals 10 because we're big boys and girls. All right, so the normal force is the only thing we don't know. We can say 1250 minus 610 sine of 35. Right, I just moved everything over, is equal to the normal force. So we need to know what it is. So 610 sine 35 is 349 minus 1250. Switch the sign to my head is 900 newtons. The normal force is 900 newtons, right? Because it's got a partner here helping it. This upward here, 900 plus whatever this is equal to 1250. So we can put that in here. 900 times 0.305 is equal to the force of friction. The normal force times the coefficient of friction times 0.305 is equal to 274.5. So 610 cosine of 35 minus 274.5. All right, so 610 cosine, I wish I would have done that already. That'd be nice. Is equal to 500, basically, minus 274.5. Minus 274.5 is 225. So let's just say that the net force is equal to 225 divided by 125 is equal to 1.8 meters per second squared. The acceleration of box. The amount of work done is equal to the net work, I suppose, which is going to be the net force times the displacement. Sure, how about that? The net force was 225 newtons times 3.5 meters. $788 joules. I'm off camera. Perfect. Love that. Yeah, I guess that's the advantage of the Cami method of doing this, but it is a big pain in the butt. So, all right, there you go.